Yeah, just solve it as is, right? Don't do anything else. What could be a problem here? Yeah, there's no x1. I can't possibly get a pivot in the upper left-hand corner, right? Okay, so maybe tweak it slightly. That's what we mentioned. What if I tweak it slightly? When I divide by epsilon, what's it going to do to all your coefficients? Make them huge, right? Relative to the rest of them. And you're going to get that catastrophic cancellation stuff that we talked about, right? That's why you want to do partial pivoting. That's why we go to the biggest magnitude, so that we can try to mitigate those cancellation concerns. In the worst case, you get a 0 where you're trying to make a pivot. In the close to the worst case, you've got a really, really tiny number that you're trying to make a pivot. Okay? That's why we try partial pivoting. So it eliminates that cancellation part that's going to come up by making numbers really, really big by trying to make that really, really small thing a 1. So there's cancellation issues. That's why we care about that. All right. What about Newton's method? What can go wrong with Newton's method? Okay, let me ask you this. What's the formula for Newton's method? Start there. Cool. All right. Yep. It's take your previous guess and then do the subtract that ratio, right? Function over first derivative. What if you're doing optimization instead? It would be, what's that ratio change to? First derivative or second derivative, because what you're trying to find is instead of the 0 of the function, you're trying to find a 0 of the derivative. That's why it changes, right? Okay, go back to the original Newton's method. It's a ratio. What can go wrong with that ratio? The denominator is equal to 0, right? What does the denominator equaling 0 represent in this case? Graphically, what does it represent? On the graph, if the denominator is equal to 0, what kind of shape you're going to have on the original function? It's be flat, horizontal tangent, right? We're going to have a horizontal tangent. Why is that a problem? Well, maybe you've got, drawing a picture on the board again. Maybe you have, pardon me, something that looks like this. I'm trying to find this 0, but I pick maybe something really, really close to that flat spot. Remember what Newton's method entailed. We did the tangent line and then use that as our approximation for the root. Looking at that picture, am I going to find the root that I'm looking for? No, what root am I going to find? That one, right? If you start with a guess that is at a horizontal tangent, that's really bad because you're dividing by 0. But again, if you're starting at a point that's near that horizontal tangent, it's going to throw your next guess way off. Right? That's what can go wrong with Newton's method. What about bisection method? What did bisection method entail? What was bisection method used for? Well, the first thing, the thing we did on the first day of class. Okay, let me start with the example back on the board again. What if I wanted to find that root right there by using bisection? What would I need to know first? Yeah. Yeah, where there's a sign change, right? You need a sign change, correct? I need if I have a point that's above and a point that's below so that I've bracketed the root. Remember that was what we called one of the bracketing methods, right? Trying to find a spot where there really is one. Would the bisection method help you in a situation like this? Can I find that root using bisection method? No. Am I going to have much luck finding that root with Newton's method? Well, maybe. Depends on what you're willing to do for a tolerance, right? That's going to have an issue with Newton's method because I'm going to get close to that zero and then I'm going to get a really flat tangent and may throw things off depending on how we're representing the numbers. Right? But bisection definitely is not going to work on that, right? At all. Okay? Because it doesn't cross. It just touches. Bisection requires a sign change, and we don't have one there. Right? Let's talk about why we even care about least squares. There should be a couple of things that you can think of, at least, of why we might want to use least squares to represent a scenario, rather than trying to interpolate the polynomial through all of the points. Can you give me one reason why we might want to use least squares rather than polynomial interpolation? Yeah, so exactly right. One of the reasons why is because if we've got something that's getting flat towards the ends and we use those evenly spaced nodes, we start getting that really wild phenomenon, right? And it's not actually giving us an idea of what's going on with the points. Think of another reason. Pardon me. What if I collected thousands of data points? Am I going to want to interpolate that? No. In fact, if I've got 2 points that have the same x coordinate, can I even find a polynomial interval through that? No, because it's not a function, right? If I've got 2 points that have the exact same x value, I'm screwed as far as finding a polynomial interpolate, right? Polynomials are functions. I can't have the same x values on the with 2 different y values and make it a function. Right? So there's at least 3 reasons there why you might want to use least squares rather than a polynomial interpolation. Okay. So that's what I mean by the conceptual types of things, right? Why do we do what we do, right? Why do we prefer Gaussian elimination with partial pivoting over naive Gaussian elimination? How do cancellation issues? What are you always going to have issues with when you try to represent a number? Well, you're always going to have to do some rounding, right? Always, no matter what. What can go wrong with Newton's method? What can go wrong with bisection method, right? Those are the kinds of things that you need to think about. Right? You can imagine a question on the exam just asking you those types of questions. What can go wrong? One of the big themes of this class is, right, what can go wrong? How do we make it better? Right? And honestly, the farther things go along in the world, the more computations that you have to do on larger and larger data sets means that you need to do things faster and faster somehow. And you got 2 choices. You can improve the hardware or improve the software. That's all you got. Right? Or invent magic. I suppose that's number 3. Okay? That's all you got, hardware or software. So we're talking about the software side of things. Hardware, the biggest pardon me, probably one of the biggest developments recently in hardware is just using dedicated units to do computations. You can parallelize similar computations across large vectors, if you will, and vectorize things and do them all at once. turns out that graphics processing units have done really good jobs of just being able to accelerate a lot of different computations. That's the hardware side. That's why you got people doing research in both areas. All right. Topics that we talked about. You should be able to convert a number to binary. That's kind of a big deal. It's not going to be a big number because you're only going to have a calculator, right? So it's going to be relatively small if you're going to be doing computations with your calculator. Okay. Convert it to binary, be able to write a machine representation. And not necessarily single or double precision. If I tell you you've got a certain number of bits for an exponent and a certain number of bits for a mantissa, your decimal part, binary decimal part, you should be able to write the number. Okay. We also did those problems. We went on the homework, like what's the biggest and what's the smallest representable number. One of those on the review as well. So making sure that you can do those things. I'll just pull up the review so we can go over those things. Let me get on Moodle real quick. Maybe. Duo being out yesterday was a trip. Oh, nope, not going to make me do Duo. Great. That's what I like to see. Moodle. Miracle. Review. Oop. So finding a machine representation. And then like I mentioned doing, go away. I swear. Making sure that you can find the smallest and largest numbers. And again here, if you were doing something, maybe as an extra practice if you wanted to do that, because this one says using single precision, maybe you should try to represent this number using this setup. Using 4 bits for the exponent and 7 bits to store the mantissa. That'd be a good practice. Okay. It's going to involve first changing to binary. Then how do you represent your exponent, right? You only have 4 bits to do it, so you do that shift in the middle. Talked about that, right? And then, pardon me. And then you may have to lop off some decimal places on the end in this one, since you only have 7 spots to store your decimal spots. Right? Remember, we just chop off at the end. That's one of the reasons why we say we have problems with representing numbers on a machine. Right? Here's one with bisection method. Again, notice this is indicative of a type of problem I would give you on the bisection method. I would give you an interval to start with. You should be able to check that there really is a root. What do you have to do to check that there really is a root? I mentioned it before, what we did for a bisection method. Sign change, right? We just show that f of 1 and f of 2 have different signs. You should probably also note something else. What has to be true about your function? Did it have a hole in it? No, it has to be continuous, right? Your function has to be continuous in order for that to work. If you've got a jump, all bets are off. Okay. Right. So you should note that, obviously, if you're going to do this in this case, what do you need to do first? I got sine of x equals x squared minus x. Do I have a single function there? No, I need to move everything to one side, right? We need to define a function that we're trying to find a root, so it needs to be equal to 0. Okay. All right, but here it's just a matter of plugging things in. What do you use for the C value here in the bisection method? What do I use here? What's the next point that you try? Bisection. What do you do? Midpoint, right? Use the midpoint, right? It's called bisection method for a reason. All right, we're bisecting the interval now. All right. Again, like I said, this would be a pretty standard type of problem. I would ask you or show that there's a root, and then use bisection method to try to find the root. Okay? I'm not going to ask you more than do a couple of steps. Okay. There's no point in it. If you can do a couple of steps, you can do multiple steps, right? Same philosophy there. All right. I have Newton's method on here. What I don't have on here is secant method. Rather than using the derivative in the denominator, for secant method, what do you use instead? Slope of the secant line, right? Use your previous two guesses and use slope of the secant line. Again, for something like secant method, I'm not going to make you do more than like 2 steps. Okay. There's not a lot of time, and 2 steps tells me if you understand what the method looks like. Okay. Also, Newton's method, not only can we approximate a solution, we can approximate an max or min, right? The formula doesn't change much. You just do the derivative over the second derivative. It's the same formula. Okay. We got a couple of those, or at least one of those down there. Pardon me. I guess I do have a secant method on there. I forgot about that. One thing I don't have on there that I need to be able to do is golden search. Remember golden search? You bracketed a minimum, and then you use the golden ratio to try to re-bracket. Okay. That one I'm literally going to ask you 1 step. Okay. Can you do the next step? Okay. Because there are a lot of computations. You've got the golden ratio in there. You've got to make sure it's scaled appropriately across your interval. And then you got to divide your interval up, and then you need to figure out which one you have to take. I mean, there's a lot going on in golden search. So, one step. Okay. Like I said, a lot of stuff going on with it, right? You got. I'm going to give you the bracket. I'm not going to tell you have to go find the bracket what you need, right? I'm going to tell you it's in between these 2 points. Tell me what you get when you try to shrink it to the next interval. That's not going to be a trick question at all. Literally, you start with 1 bracket and make it smaller. Okay. All right. As far as least squares goes, no, we'll come back to the polynomial. As far as least squares goes, I'm not going to, this one has you going through all of it. I'm not going to make you go through all of it. Make sure that you can set up the normal equation. Remember that's matrix system? Make sure you can get to that. Make sure you can rewrite your system to that. Okay. So let me flip over here to the key real quick. Maybe it loads. Actually, this is not very great. This is not great. Here is setting up the least squares line with your matrix A and computing your A transpose A here. That would be what's on the left side here. On the right-hand side, all I need for this is that you would do your A transpose is 2 rows. What am I doing? 1, 1, 1, 1, 0, 1, 2, 3. And your B is your -1, 5, 2, whatever the y coordinates are. 6. And do that computation. And then stop. Just set it up to there. You don't have to worry about trying to find the inverse and doing all the rest of the multiplications. Okay. Just to get to that point. There's enough, well, computations up to that point. Okay. All right. What else did we have? Making sure that you can do your polynomial interpolations. Making sure you know what the Lagrange cardinal polynomials are. Making sure you know how to do divided differences in particular. You do not, I repeat, do not need to multiply out all your polynomials. Just set them up, okay? All right, so for example, again, if I kick back over to the key, oh, geez, that was fun. There it is. This is, I don't expect you to multiply all of this out. Okay, leave it. All right, let's get this set up. Okay. This shows me you understand how to write the Lagrange cardinal polynomials to get you to interpolate the polynomial. Simplify your fractions here a little bit. That's it. Well, this is fine. Okay. Don't try to multiply it out as a nice polynomial or a nice looking polynomial. Likewise, when you do your divided differences here, don't bother multiplying all these things out. Literally just write out the polynomial. Okay. And your numbers should come out to be nice. I don't need a bunch of fractions in there. Okay. Your numbers should come out to be nice when you're done. Again, not trying to be tricky. Okay. Literally, can you do the methods that we talked about? Okay. Any questions at all? No. Nope. No Excel, no computer, just your calculator. This is why I said there are going to be 1 or 2 steps, right? Not going to be a bunch of steps to do. Make sure you can do what I mean. And for a naive Gaussian elimination, I know the one on the homework, you were carrying out everything with a bunch of decimal places. Again, literally 1 step, okay? Do you? And the questions are going to be more like, do you know what I mean by these words, right? If I say, carry out the first step in naive Gaussian elimination, then you're going to get a pivot in the upper left-hand corner and eliminate down below it, right? If I ask you to use partial pivoting, then you're going to find the biggest thing and make it the pivot and eliminate the stuff. Okay. And I'm not going to make you do more than 1 column as far as a row reduction. Okay. There's enough computations in a row reduction the way it is. Okay. And I'm not going to make you do anything bigger than a 3x3 system. If you can do it for 3, you can do it for 10. Okay. There's no point in making you do extra work for no reason. Okay. All right. So again, focus on your methods. It's not going to be long and involved, right? But make sure also you understand the concepts about behind what we do things the way we do them, why we do it, what can go wrong. Okay, and the short answer little thing. The whole reason why we study this stuff. Any questions at all? Any more questions at all? I'm not looking for it to be nasty. Okay. That's what the homework's for. That's what your project's for, right? That's where the nasty is. This should come in, okay? Not what you have to do on in-class quiz, test, whatever you want to call it, exam, assessment. All right, so let's talk about a little bit of new stuff. This will not be on your exam, obviously. All right, so what we want to talk about now is something that you probably talked about in Calc 2 a little bit, and that's numeric integration. We're going to approach it slightly differently. Pardon me. Goodness, apologize. We're going to approach it slightly differently. We're going to approach it from the standpoint of, rather than doing it from a geometric perspective, we're going to approach it from a perspective of, how can we make this easy for a certain class of functions, and then see what it looks like. Okay, so in Calc 2, you had midpoint rule, trapezoidal rule, Simpson's rule. Okay, you motivated all of those things by geometric shape, and that's what you kind of did when you first start doing integration in particular, right? If you think about what we mean by the integral, you have some function on some interval. You slice up the interval into pieces. You make a bunch of rectangles that are based at that on those intervals and pick some point. Like that, right? Make a bunch of rectangles and say that the integral from a to b of f of x dx is a limit of a sum of a bunch of rectangles where you've got the height is given to us by taking some value and plugging into the function, and the base is given to you by whatever the width of the subinterval is. That's what you do. You start that in Calc 1. You do applications of this in Calc 2, right? You should have seen this. Good news is we're not going to do it this way. Okay? But this is what you did in calculus, right? You have some, this is what it was motivated by at the very least. You had some function sitting above the x-axis, and you asked how much area is between that function and the x-axis. We said, we don't know. It's got a curved boundary. Curved boundaries are hard. Before calculus, the only formula you really had for something with a curved boundary was a circle, right? Every other area formula you have is all line segments, right? He said, it's hard. I don't feel like doing it. I'm like, no, you really need to do it. Okay? Okay, fine. We'll try to do it. What can we approximate it with? Okay, how about rectangles? Right? Those are easy shapes. Turns out that was a good thing to try. Okay? Bad thing is it's not very good in practice. Okay? A lot of computations to make it better and better. You have to make those things get closer and closer, right? Got lots of things. Limiting is hard. Let's see if there's other ways that we might be able to approximate these things better, or at least more quickly. Okay? And approach it from a different idea. So trying to come away from the geometric concept of it and try to go more into a how can we do a nice class of functions easily? Okay? Try to make exact computations on a nice set of functions and use that as our approximations. Okay? That's the motivation. Right? Now, again, you may have done a couple of these rules that we're going to see today. You may have done a couple of these rules that popped out from other geometric shapes. You probably talked about trapezoidal rule, right? Remember, just to draw one small picture here. For your trapezoidal rule, you probably talked about having a point and having well, that wasn't a very good trapezoid. Let's try this again. And having a point and then just connecting it with a stick there, right? And then doing the area underneath that stick as your approximation. That was trapezoidal rule, right? You probably also talked about Simpson's rule, where you picked a third point and then used a parabola as our, well, I missed that other point. Used the parabola that way and found that area, right? What we're really doing here, even though we thought about it from a geometric perspective, what you really are doing here is what we're going to talk about. If I start with those 2 points at the end point and draw the line between them, I've taken a degree 1 polynomial through those 2 points. I found a polynomial interpolant for those 2 points, right? Which is essentially what you did for trapezoidal rule. For Simpson's rule, rather than doing a line, you did a parabola, which required 3 points. Again, finding a polynomial interpolant. Okay? So that's going to be our motivation. So that we refer to this as what's called Newton. Oops, let me change my color back. Newton-Cotes quadrature. And in general, it's called quadrature. And the idea behind this is use equally spaced points and a polynomial interpolant interpolant is just a fancy name for the polynomial that goes through all the points. Okay. Use a polynomial interpolant to approximate the integral on the interval. So quadrature is just a fancy name that we use for doing this process. We have different types of quadrature. We have Newton-Cotes. We have another one I'm not remembering off the top of my head. Then we also have Gaussian quadrature. Gaussian quadrature would be another one of those. Hey, you could do extra study on that particular thing as your final project, for example. All right, so this sounds a lot more complicated than it really is. Okay, so to make this a little bit easier to start with, let's say we want to approximate the integral from 0 to 1 of f of x dx with two equally spaced nodes. Node is what the word they use instead of points. So when you do quadrature to approximate integrals, you use nodes rather than points. Isn't that very exciting? Okay. All right. So this is where we're going to start. We're going to do this integral. We're going to start from 0 to 1. We're going to do this to get our general rule, and then we'll talk about how we can scale it to other intervals. Okay? That's the idea. All right. So two equally spaced nodes. All right, well, what does that really mean? Well, if I've got some function on the interval from 0 to 1, whatever that function happens to be, the only way I'm going to get equally spaced nodes and cover the entire interval, that's all the other part of this, I want to make sure I cover the interval, is that I'm going to use those 2 points. That's what equally spaced is here. If I'm going to cover the entire interval, I better have points at the endpoints. That's the only way it's going to be equally spaced. And that just means that if I go from one node to the next and then go to the next one, they better have the same distance between them along the x-axis. Okay? Well, there's only 2 points. Now, technically, if I use 2 points, I could technically go anywhere in my interval and do this. Okay? I just may have to weight it differently. We'll talk about that a little bit later. But right now, it makes sense that I would want to try to use my endpoints, right? At least I think it makes sense. All right. So if I have 2 points, what is the largest degree polynomial that interpolates those points? 1, right? Because it's always the degree is 1 less than the number of points we have, right? Okay. All right. So what the idea here is, we want our quadrature rule to integrate all constant functions and all linear functions exactly. Okay. Why did we stop at linear? Well, in this, it's for this specific case. Okay, we stopped at linear polynomials because that's the largest degree polynomial that we can interpolate the points exactly. Okay. All right. All right, so what do we mean by the quadrature rule? Well, what we really mean is that I want to be able to plug the points into the function that I am given to give me an approximation for the integral. I don't want to plug it in some random spot, right? So what this actually says is that if the function I'm given is a constant function, then I should be able to plug in the points into that function and it gives me the right answer. And if I'm given a linear function and I just plug in the points that I'm given into the function, I should give me the right answer. And then I have no guarantees on any other type of function. That's what this means. Okay? All right, so let's think about what this implies. So what this means is that, so given f of x, what's we're given, right? Our quadrature rule in this case looks like it'll be sum w1 times f of 0 plus sum w2 times f of 1 in this case. Okay? Why that? Oops. Yeah, that's a 1. That looked like a 0 when I look back up. These are the 2 points that we started with, right? Okay? Those are the points that we're going to plug into the function that we're given. We're going to have some weights. We usually refer to these as weights associated with them. That's why I call them W1 and W2. Okay? When we do this computation, this is what's going to give us the estimate for the integral we're trying to do. So again, this is important, and this looks like your other formulas that you've talked about in calculus. The idea is we don't have a lot of things to work with. We have the interval and we have the function, right? So we're using the interval and the function to give us an approximation for the integral. And we're going to come up with some formula that allows us to do that. That's the idea here, okay? All right. Now again, we want this to integrate all constants and all linear functions exactly. Well, what 2 functions in particular can you use to generate every single function and every linear function? There's 2 functions that you can use to generate all of them. 2 very specific functions that you can use to generate any ax plus b. What 2 functions can you use? 1 and x, right? Something times 1 plus something times x generates all polynomials of degree 1. Okay? Now, why is that helpful? Well, integration is linear. It breaks up over sums and constants pull out. So if I know how 1 integrates, I know how every constant integrates. If I know how x integrates, I know how every multiple of x integrates. Therefore, I know how every linear polynomial integrates. Okay? So, using that, we solve the following. I said that I want to integrate all constants and all linears exactly, right? So I want the integral from a to b of 1 dx to equal some weight times f of 0 plus some weight times f of 1. And I want the same thing if I put an x in here. Now, I've written an arbitrary x over on the right-hand side. But remember, that's not an arbitrary f. The f is the function we're trying to integrate, right? So in the first equation, the f is that. In the second equation, the f is that. Okay? All right, so let's see how this simplifies. Let's actually, honest to goodness, integrate the left-hand side. What do you get when you integrate 1 from a to b? What answer do you get? B minus a. Good. Now, on the right-hand side, remember, the function we are given is 1. So what's f of 0 if the function we are given is 1? 1? And what's f of 1 if we're given the function is 1? 1. Good. It's constant, right? So our b minus a here needs to be w1 times 1, or just w1, plus w2 times 1. Okay? That's the first equation we need to solve. Or, sorry, the first equation in our system we need to solve. Let's do the second one. What do you get when you integrate x from a to b? Careful. Careful. It's not quantity squared. It's b squared minus a squared. There you go. It's b squared minus a squared over 2, right? Because it's 1/2 x squared. All right. Now remember again, in the second case, the function we are given is x. What's f of 0 if the function is x? 0, right? So this will be w1 times, I'm just writing it out so you see where the equation's coming from. What's f of 1 if the function is x? 1. Okay. Oops. Times 1. All right. Oh, yeah, that's right. This okay? All right. So this makes it a little bit easier. This second equation just says that W2 is b squared minus a squared over 2. All right? What do we get in the first case here? Well, this one says that W1 plus b squared minus a squared over 2 is b minus a. This is not working out the way I wanted to. It's okay. We'll figure it out. I feel like I did something wrong somewhere along the line here. Anyway, all right. So our W1 then is b minus a, and then we flipped around, plus a squared minus b squared over 2. Oh, I know, that looks weird. I think. All right, so let's put this together and see if we can see what this looks like and why it looks like our trapezoidal rule. All right, so our quadrature rule in this case, integral from 0 to... that's my problem. I'm using b's and a's. That's my problem. That's my issue. Okay, let's go back to this. I used a to b. What's my interval I'm talking about on this one? 0 to 1. I really should have had zeros and ones here, right? So let's go back over here using the zeros and ones. If I use zeros and ones, what's W2 equal to? You put a 0 in for A and a 1 in for B. What do you get? A half. Good. And if I do the same thing over here, this is, so I would have, let's write it this way, W1 plus a half equals 1, right? Right? That's why it was looking weird. I forgot to put the numbers in. W1 equals 1/2 as well, right? Yep. Okay. So our quadrature rule then, you write back over here, your I, which was the integral from 0 to 1 of f of x dx, is approximately 1/2 of f of 0 plus 1/2 of f of 1. And this makes me feel much better because this is exactly what it should look like. Does that look like the area of a trapezoid? So let's think about what the picture looks like. Oops. So I've got some function. Let's say here's my 1, here's my 0. I've got a line that goes this way. I didn't make it look very trapezoidal. Remember your formula for your trapezoid is 1/2 the height times the sum of the bases? Right? But this is your height. What's the height in this case? It's 1, right? This is your f of 0. This is your f of 1. So I have 1/2 times the height times the sum of the bases. I really do have the trapezoidal rule here. Does that make sense? The trapezoidal rule, 2 points on one interval, right? We're going to talk about how we put these rules together to make what you see typically in Calc 2, but that literally is what we have from those 2 points on one interval. Okay. Is this okay? Now notice that we were not motivated by geometry, right? What were we motivated by? The algebra, right? We were motivated by, I've got 2 points. With 2 points, I can interpolate with a degree 1 polynomial. So let's integrate all polynomials of degree 1 or less exactly. And we set up a system of equations. Okay? So let's do that for the next rule. Let's, instead of doing 2 points, let's do 3. Let's see if we can approximate integral from 0 to 1 of f of x dx with 3 equally spaced nodes instead of 2. Now, not all quadrature rules have to use equally spaced nodes. Not all quadrature rules need to include the end points. We're doing that now. Okay. All right. So if we include the endpoints and we want equally spaced nodes, well, here's 0, here's 1. Where better my third node go? If they're going to be equally spaced. 1/2, yeah. I better use 1/2, right? All right. So those are the 3 points we're going to use. Motivated in the same way that we were motivated before, I have 3 points. What's the highest degree polynomial that we can use to interpolate 3 points? 2. Okay, so motivated by the same way we were before, we're going to make sure that our quadrature rule integrates all constants, all linears, and all quadratics exactly. Okay, we have 3 points. We can go down to degree 2 for our polynomial interpolant. Right? So we're going to make sure that we integrate 1's, x's, and x squareds all exactly. Okay? And again, I can generate all quadratics by a 1, an x, and an x squared. That's what we're going to use. Okay? So we're going to set up a similar system of equations like we did before. We want the integral from 0 to 1 of 1 dx to equal weight 1 times the left node, function value evaluated at the left node, weight 2, f of 1/2, weight 3, f of 1. What's the next equation we need to set up? Yeah, one for x. And the last equation we need? X squared. Good. Notice that it works out nicely that we get a nice square system here, isn't it? Shockingly enough. All right. Let's simplify our system here. Let's do the left-hand sides first. What's the integral of 1 on the interval from 0 to 1? Just 1, right? What's our integral of x on the interval from 0 to 1? 1/2. And the integral of x squared on the interval of 0 to 1 is going to be 1/3, right? The x cubed over 3. You plug in 1 and plug in 0. Okay. Now again, remember, it looks like we have an arbitrary f the way I've got it written, but I don't really mean it's an arbitrary f, right? This f again corresponds to that 1. This f corresponds to the x. This f corresponds to the x squared, right? Okay. So, using that, what do you get for the right-hand side of the first equation? Good. Because it's the constant function 1, right? So no matter what we plug in, we're always going to get 1 out. So it's W1 plus W2 plus W3. Okay. What do we get for the right-hand side of the second equation? Yeah. Good. Yeah. So it's 0 W1, because we're plugging it into X, right? So it's 0 W1, 1/2 W2, 1 W3. So we get 1/2 W2 plus W3. Where do we plug the numbers in for the third one? Where did the 0, 1/2, and 1 go this time? X squared. So what do we get for our coefficients for our W1 and W2 and W3 in this case? Or what do you get for the right-hand side? Either or. Good. Yeah, you get a 4th W2 plus W3. 0 squared, 1/2 squared, 1 squared. Right? So now we've got a system of 3 equations and 3 unknowns. We just need to solve it. Okay. All right, so let's see what we get here. When we solve this, well, let's look at the second 2 equations here. I've got a W3 in both of them. So let's just subtract this way. If I just subtract those two, equation 3 from equation 2, what do you get for your equation that's left? Well, I would just subtract down. I would do 2 minus 3. Doesn't matter, but. Ooh, yay. Okay. Yeah, 1/6 equals 1/4 W2. So W2 is equal to. Good. 2/3. Good. From that, we should be able to figure out W3. Use the second equation or the third equation. Doesn't matter which. I'll use the second equation. 1/2 equals 1/2 times 2/3 plus W3. What do you get? The 6th? Good. And then finally, if we use the first equation, 1 equals W1 plus 2/3 plus 1/6. What do you get for W1? A 6. Good. So the quadrature rule that we just came up with is 1/6 f of 0 plus 2/3 f of 1, f of a half, plus 1/6 f of 1. This is referred to as Simpson's rule. The top one was, the previous one was trapezoidal rule. This is Simpson's rule. Now, if you remember Simpson's rule back from Calc 2, assuming you covered it back in Calc 2, this might look a little bit different. Oh, great. Thanks for telling me. I'm so happy that my battery is low. How much battery is left? 6%. Oh, well, my recording might die. Who knows? Got 10 minutes and 6%. Let's see what happens. All right. Let's think about what the Simpsons rule looked like back in Calc 2. You may not remember. That's okay. Not you don't teach Calc 2 like I do, so I probably remembered a little bit better. But you might remember there was a 4 and a 2 and a 4 and a 2 and a 4 and a 2 that alternated back and forth. Now notice we've only done one interval, right? Your trapezoidal rule also had a bunch of 2's in the middle. If you remember that at all. Okay. We've only done one interval, which is why we don't have that. We'll talk about how we put those together in a little bit. Okay. But let's think about what the pieces were. If you remember your Simpsons rule back in Calc 2, looked like delta x over 3, and then you had an f of x naught plus a 4f of x1, and blah, 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 right? As you went along. With a 2f of x2, and so on. It's just alternated back and forth. But again, we're only doing one interval here, right? Remember, your delta x is the width between two endpoints. Two consecutive subinterval endpoints, right? Let's think about how we set this up. We did equally spaced nodes on the interval from 0 to 1. We did 3 nodes, right? What would be your delta x in that case? A half, right? Your delta x would be a half here, wouldn't it? Okay. So looking up here, if I pull out a 1, well, I can pull out a 1/6 out of everything. Let's do that. I'd have f of 0 plus, if I pull out a 1/6, I get 4 f of 1 and an f of 1/2. Darn it. And an f of 1. I'm not writing that very well because I've got it written off to the side there. Or if I pull out a 1/6, that's what I'm left with. That would be 1/3 over 2, or the other way around. 1/2 over 3. That looks like your delta x over 3, doesn't it? And then if you remember your alternating bit from your Simpsons rule back in Calc 2, it went 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. But that was you had multiple intervals, right? If you only had 3 points, it would have been 1, 4, 1, which is exactly what we have. So this really is the same as Simpson's rule that you did in Calc 2. Again, motivated from a different perspective, right? We were trying to do some algebra versus trying to make the geometry all work. Okay. So motivated slightly differently. All right. So this is what's referred to as Simpson's rule. And you can continue with this idea. Okay. You could do 4 equally spaced nodes, get a new rule. You could do 5 equally spaced nodes, get a new rule, and so on down the line. Okay. Questions on it at all? All right. So just to talk a little bit about how you can scale these things, and then we'll do some more stuff on next week because we'll need to review this anyway. We went from the interval from 0 to 1. What if we wanted to go from a different interval from A to B? Okay. Well, we can talk about how we can move those around. So say we had 0 to, just say we did from 0 to 1 of f of x dx, and we had some quadrature rule that I'll write as a sum from I equals 1 to n of w sub I f of x sub I. Write it that way. Let's say that was my quadrature rule, whatever it happened to be. And I wanted a new quadrature rule on A to B of f of x dx. I wrote equals. Really what I mean is approximately equal to, but I don't want to write my wavy pieces there. But what we can do here is basically a U substitution idea and make this integral look like this one. Just scale it. Okay. So in particular, there it went.